All right. Besides Ibrahim spouting nonsense, any questions? Okay. We last left off. All right, so we had Maxwell's equations. What are the chances? Ooh. Today's class is sponsored by the color blue. And whatever this decides to get. So the two of Maxwell's equations that we really care about are, if we add up all the magnetic fields around the loop, that's going to be equal to U naught I, that's Ampere's law, and that's I enclosed, plus U naught epsilon sub naught, change in the electric flux over time, and then Lenz's-Faraday's law, if I add the electric field dot delta L, that is equal to the negative change in the magnetic flux with respect to time. And that marker is not going to last us.
The mu in both mu's are the same?
Yes, that is the permeability of free space, the 4 pi times 10 to the negative 7th decimeters per ampere. Tesla said it right the first time, I think. And epsilon sub naught, the permittivity of free space. And I'm going to go get markers. Well, you contemplate that. All right, and we talked last time conceptually about how magnetic field can propagate an electric field, which can propagate a magnetic field if we have this constant changing thing, self-propagation. So let's take a look at that. Suppose I have an electric field, and this is some ambient value of electric field, and this magnitude would be epsilon sub 0. Sorry, that's an E. I'm going to do E sub m for maximum, just so also it doesn't get confused with epsilon sub naught. This is the maximum electric field. And then in and out of the board is the magnetic field, which I will attempt to draw like this. And just recognize that black line is supposed to be going in and out of the board. Please draw your three-dimensional drawing, however it's appropriate in your notes. So what this line means is that at this point right here, that my magnetic field would be that long, and then it gets shorter as I go to the left, and it gets, well, if that's the peak, it's going to get shorter as I move to the right.
Does it actually happen like that? Like it's just the flip on the curve? Right.
Flip on the curve.
So
That they
yeah, like they,
yes,
okay.
yes it does.
The maximums pick each other, I guess. Like
Yes. And then so what I'm going to do is I'm going to create a Gaussian loop or an Amperian loop, depends upon which school you're from. And flip to my notes so that I don't go astray too far. Actually, let me write down the equations. So my electric field is defined by this amplitude times, just to stick with my notes, I use sine there, so I drew sine there. Sine of kx minus omega t. And my magnetic field is defined by the amplitude of the magnetic field, this maximum value, times the sine of kx minus omega t. Because they're both sine of kx minus omega t, where the k's and omegas are the same, that is just math backup for what Jack was asking about, the fact that they both are 0 at the same time and they're at maximum values at the same time. Oh, we had one other bit. Just to refresh your memory. I know the speed of the wave is equal to the wavelength over the period. I know that the wavelength is equal to 2 pi divided by the wave number. And the period is equal to 2 pi divided by the angular frequency. So this becomes 2 pi over k equals 2 pi over k times omega over 2 pi, and we end up with omega over k. That will come in a moment. Questions up to here?
So E of M and B of M, those are just the amplitudes, right?
Correct.
Okay. And I'm pretty sure what I have is right, but BM is just a sine wave in a different dimension than E is.
Right, well, I mean, the
It's the
value,
same.
M and BM are different values, they're different units, different scales. But yeah, they're perpendicular to each other.
Okay.
Now, in reality, if light's coming at you, it's not like this. The electric field is all over the place, and each electric field has a magnetic field that's perpendicular to it. So you're being bombarded by the electric field lines that are, and then there are magnetic field lines perpendicular to each of those. Now, what polarized lenses do is they cut out, in essence, a polarized lens would have slats like that blocking out any component that is perpendicular to those. So only things that go through are the parts of the light that are parallel to that. And so you basically cut out half the light. And if you played with polarized lenses, that's it, polarized sunglasses. If you take two polarized lenses and you cross them so that you have one set of, not the right term, but slats going this way, and another set going like this way, you block out all the light completely. But that's for a different, probably during class, but a different day. All right. Faraday's law. What I'm going to do is I'm going to take my Amperian loop right along there. If I sort of zoom in, I have my electric field going up, and let's see, I'm trying to stick to my color convention here of blue for the electric field. I have my electric field here and an electric field here. Where I've drawn it, it's getting bigger as I move to the right. So I'm going to label this as E, and this is E plus delta E. And my magnetic field is coming perpendicular to that. So my magnetic field, and the way, since I picked it here, the magnetic field is coming out at us.
And that's a Gaussian loop called it?
A Gaussian loop, some people will call it an Amperian loop.
Is there a difference?
No, I mean, a Gaussian surface is a three-dimensional surface, virtual, and I consider a Gaussian loop to be just a line that connects up with itself. Now, because we're using, this is based on Ampere's law, some people call it an Imperial loop.
Is this just one of those things that's like depending on the textbook? And some looks like the other one.
I'd like to say yes, but it could just be me. I think I've been calling them Gaussian loops so long that I ignore what the books call them. You know, I'll read it and they say Imperial loop, and I'll go, okay, fine, Gaussian loop. All right. Well, actually, we're using Faraday's law here. But, all right, so I've got this rectangle here. I mean, it has dimensions. This is a actual rectangle. It's a virtual rectangle, but it has a width of delta x. And for those who've had calculus, translate dx into this. And it has a height here of, we'll just say L. Now, Faraday's law here, or Faraday-Lentz's law, is we are going to do E times the length, the electric field times the length around the loop. So I'm going to start here. I'm going to go in the direction so that a right-hand rule, my thumb points in the direction of the magnetic field. So I'm going to be going around in a counterclockwise direction. So I'm going to label that A, B, C, and D. In nice tiny print. And so if I'm going to start out with writing down Faraday-Lentz's law. Equals negative change in magnetic flux with the change in time. And right off the bat, I switch my letter that I'm using. Let's try some consistency. Well, this is going to be the electric field along A dot the change in length along A plus the electric field along B plus delta L along B. Nope, not plus there. Dot the electric field along C dot delta L along C plus the electric field along D dot delta L along D. And that's going to be equal to the negative change in the magnetic flux. Well, what's the formula for magnetic flux? Assume the magnetic field is constant. Pardon?
B cross there.
Ooh, close. Not cross.
Dot?
Dot. Oh, is that what you said before?
No, but I'm correct.
Okay.
Is it dot?
It is dot. The change in B dot A over delta D. So let's concentrate on the left-hand side. Which of those dot products are going to be equal to 0?
C.
Why?
Well, there's no length on it, I don't think.
There's no length on it? The length would be L.
Well, right, but I don't think there's a magnetic field. Oh,
We're doing electric field.
electric field here.
Oh yeah, there's the electric field along B is E plus delta E.
Also, technically, there's like small lines going all the way through.
Yeah, there's electric fields that I haven't bothered to draw. Because if we were doing this formally, this would be infinitesimally small, so.
I see what you're saying.
Think about dot products. When is the dot product equal to 0?
When it's perpendicular?
Yes. So along which segments will the line vector be perpendicular to the electric field?
A and C?
Yep. So that is 0, and that is 0, because the electric field is perpendicular to delta L. So that leaves us, and the same reason here. So along B, we definitely have an electric field because my line segment, because I'm going counterclockwise, so I'm going up on the right, same direction as my electric field, and so this becomes E plus delta E times L.
What are they parallel to? Or-
Right? When I'm doing in essence a line integral, but I'm doing a line sum without calculus. So along each segment along this path, I'm taking the electric field and multiplying, doing a dot product with a length vector. So I'm starting at the lower left-hand corner. I then go that way, this way, that way, and that way. This would be my delta L sub A, delta L sub B, delta L sub C, delta L sub D. So my delta L for part A is moving to the right, but my electric field is up. Along B, my delta L is up, as is my electric field, and so on.
So they're parallel to the electric field?
Along D, yes. And along D,
Yes.
it'd been nice if someone had said, hey, no, they're anti-parallel, but sure.
Would this actually be easier if we had calculus?
Yes.
Would it just be, instead of infinite sum, be integral, and then instead of all the deltas, it'd be D?
Yes.
Okay.
Feel free to put that into your notes. Because even with calculus, though, the integral ultimately is going to break down to this. Because integral is just a big sum. It's an infinite sum of infinitesimally small pieces.
So we just have an extra step where we have to break it up to find that?
Yeah, and also with calculus, doing the slopes of functions becomes hopefully trivial. All right, and this last one, minus, since they're in opposite directions, E times L. And that's equal to, well, over here, my magnetic field, with this rectangle is such a small area here, we can assume that the magnetic field is constant, so negative B, as well as B and A will put in the same direction, because remember the area vector is perpendicular to the surface. So B times, rewind some of that. My area is constant, so it's coming out. My magnetic field is almost constant, but not quite. So making that assumption was a mistake on my part. So this is A times delta B over delta T. Well, the area vector, what is the area of that rectangle?
Length times width.
Which, in terms of how I've labeled it,
L times delta X.
L delta X times delta B over delta T. Now, let's simplify it a little bit. We'll distribute the L. So I have EL plus delta E L minus EL is equal to negative L delta X delta B over delta T. On the left-hand side, ELs cancel out. Yes?
So the one right above it in the first equation, that minus E, is that an L?
Yes, that is.
Zero?
That's an L.
Okay. I was looking for this.
Why did they cancel out on the left-hand side?
Because I have EL and negative EL.
Oh, that's the part that gets out.
The delta E stays. So all of that breaks down into L delta E equals negative L delta X delta B over delta T. My L's cancel out. And I'm left with an even simpler equation, which is going to require us to do slopes. All right. Any questions up to there before I go to a new screen? Carolyn?
I'm confused about how you got two different, like the positive and the negative EL.
All right, I'm doing dot products. Vectors in the same direction. Do the quick reminder. If I have A and I have B, and I do A dot B, then it's A, the magnitude of A times the magnitude of B times the cosine of the angle between them. Which means that if they're in the same direction, the angle is 0, and so cosine of 0 is 1. If they're in opposite directions, I'm dealing with pi, or 180 degrees, and the cosine of that is -1. So when I'm going around my loop here, in this last segment, because again, my line integral or line sum, I'm going counterclockwise. So in this last segment, my line is going down, but my electric field is going up. So the dot product is negative.
Okay, and then where did the positive one came from?
From over here,
Oh,
because
okay.
again, I'm going to the right and then I'm going up in the same direction as that electric field. Then
Do you
over.
have to always go counterclockwise, or could you?
It ultimately comes down to a right hand rule. I go in the direction so that my thumb points in the direction of the magnetic field. Other questions? So I've got delta E. So I'm left with delta E is negative delta X, delta B over delta T. So I'm going to divide both sides by delta X. So I have delta E divided by delta X is equal to negative delta B over delta T. That first, on the left-hand side, that's the slope of my electric field versus position graph. On the right-hand side, that's the slope, or the negative of the slope of my magnetic field versus time graph. Well, this is what we spent time doing the other day. I got my electric field changing with respect to position. What would it be?